mic switched on? Yeah. Okay, clicker. Okay, so my name's Rhys. I work at the Financial Times as a principal engineer. For much of the last 2 years or so, I focused on performance and front-end architecture of FT.com. So I'm going to tell you a bit about the solutions we've come up with and the problems we came up against. So there is FT.com. The Financial Times is one of the leading business and economics news publishers in the world, and FT.com is the main online presence. So about 4 years ago, we decided to rebuild it from scratch, and about 2 years ago, we launched it to the wider world. And one thing we're really proud of is it's really fast. This is a project by a consultancy called Hearst NP, comparing the load times of all the different news websites in the world, and FT is consistently in the top 3. And just a quick plug, we're always hiring. We've got loads of mainly Node.js and front-end web dev jobs going. So if you're interested in applying, do come and speak to me after. So the things I am going to cover today, I'll tell you a bit about our tech stack, the decisions we've made, why we've done them. I'll go into a couple of examples of how those choices can sometimes conflict with optimizing performance. So 2 things, I'll talk about the paywall and how we optimize our very complicated front-end stack. But the main motivation for speaking today is to share some examples of failure, because it can be very easy coming to lots of talks thinking, yes, I should do that optimization and that and that and that. And it's not always that easy, so I think it's quite important for some people to share where we go wrong. So, first of all, this is the old FT.com site. It was called Falcon. I'm sure it was state of the art someday, but by the time we rebuilt it, it was starting to look a bit dated. And it was also really, really slow. You can see there it took about 9.5 seconds to load a page going by the Lighthouse audit. But what you couldn't experience as the end user was actually really difficult to work on. So we tended to release once a month. Those included lots of bugs. We maintained multiple environments. And because that was such a poor developer experience to get stuff onto the site, loads of backdoors developed, so anyone could chuck any sort of junk onto the site by circumventing these routes. So that was a pretty bad situation as a developer, so we formed a new team called Strategic Products, which were aimed at changing all that. And that team eventually grew to become the team that built the new FT.com. And this is sort of a guiding principle of that team, that if we ever need to start from scratch again and rebuild FT.com, throwing everything away, then we've gone badly wrong. So that's the thing we want to avoid. We always want to make it easy to release good code responsibly onto the site. So to make that possible, there was a few decisions we made. So first of all, we insisted on having, the tech team insisted on having a lot more control over what went onto the site. So there are no tag managers on the new site. There's no very little third-party code. And it's very difficult for someone just to have an idea and chuck it on the site without sort of clearing it with the tech team and other departments. So that improves all sorts of things, security, performance, and user experience. And it maybe sounds a bit confrontational, like we're insisting on control, but the business knew we'd got to quite a bad place. So there's actually a lot of buy-in from all sorts of stakeholders. So then the first technical decision is we streamlined how we get code onto the site. We have one environment, which is production, and you merge your code into master, and 10 minutes later, roughly speaking, that will be serving production traffic. And all that process is automated. So the benefits of doing that are smaller releases means bugs tend to be quite isolated, easy to find and to fix. As we only have one environment, we don't have problems with configuration not being equal in different environments, so we avoid those kinds of bugs. It's really easy to experiment. You can release an MVP. If something's slightly wrong with it, you can do another release 10 minutes later and 10 minutes after that. So it's quite good for innovation. And it's really rewarding to be releasing stuff into production all the time. I'm sure I'm not the only one who's worked on projects where you work on something for 6 months and then it gets canned. This is just a great motivating experience that you can release code every day. Something we do to make that possible is we use feature flags. So feature flags tend to be used to switch features on and off. What we do as well is we use them to hide work in progress features. So we can release terrible stuff onto the site. It's behind a flag. We QA it in production. We wait until all the stakeholders say, yes, this is a great feature, you can release it. Then we switch it on for everyone. And that kind of gives us confidence to just have this one production environment, and we don't have to worry about messing everything up for everyone because we've got feature flags to protect us. On the architectural level, we embrace microservices. That's a very rough diagram of what ft.com looks like under the hood. About 100 services there. So breaking our stack up into all these little microservices, the benefits of that is it breaks up your code into comprehensible pieces, which is a lot easier to work with, easier to deploy, easier to scale, and if something goes wrong with one of them, that tends to be quite isolated, so you don't end up bringing down the entire stack. On the front end as well, we break our code base into loads of little pieces. Our design systems library, I suppose, is a big set of components called origami. Let's get some water. So each page on the website will typically use about 30 or more components, everything from a font loader to a form to a pop-up. And again, the benefits of doing this are it keeps everything in maintainable small pieces, which are easier to understand and develop and release. It also means we can share this code between lots of sites. So ft.com is just one of dozens of sites that Financial Times maintains. And it gives us consistent branding across all its sites. And it also means that the high quality stuff we do in these components, such as accessibility, they get shared among a lot of sites developed by all kinds of people, including third parties. So in general, what these things have in common is they enable us to release good quality software quickly and with confidence. And getting to that place was really hard won. We started off at Falcon and we completely rethought everything. And we don't want to let go of those achievements easily. But when you try to optimize performance with a stack like this, it's not always easy. So I'll tell you about a couple of examples of how we've dealt with that. So the first one is the FT paywall, which we use like the rest of the stack that's built using microservices. So let's talk about the sort of principles first. The critical path, you hear a lot about it with respect to CSS, inlining critical path CSS. But more generally, the critical path means every request that you need to respond to in order to serve something useful to your end user. And more microservices means you end up with big chains like that. Every microservice adds a little bit of latency. So in theory, microservices should be bad for performance. But what you can do to improve that is use caching. So if you add a caching layer, then not every user request has to go all the way down the stack. And then making your critical path performant becomes a question of, can you improve your cache hit rate? So the paywall of ft.com means you come in on an identical URL, and depending on who you are, whether you're logged in, what your IP address is, how often you've been to the site recently, a decision will be made whether to show you a barrier or an article. So that involves a lot of really deep business logic, but for a caching layer to work, you kind of want it to be nearer the top at quite a superficial layer. So how can we cache the decision whether to serve an article or a barrier? So this is sort of the naive approach. User comes in with a cookie. That goes via our CDN fastly, which is also our main caching layer. Hits the application. The application works out whether to serve a barrier or to serve an article. And then it says, okay, I've made this decision based on the cookie. So I'll add a vary header of cookie, send that back up to the user. And that gets cached in the CDN. But because it varies on the cookie and every user has a unique cookie, that means that cached object is not going to be reused by anybody else. So what we do to improve this, Fastly have a nice feature where you can restart a request, which means you go into the CDN, you contact some application to get some extra information, then you redecorate the original request with that information before sending it to the back end. So the service we use to do that we call preflight. So what preflight does, it takes that request from the user and it converts it into a bunch of headers. So for instance, the cookie has a session token in it. From that, we can just say true or false is the user authorized. So then we get a set of a few headers with a few values, and we use them to put each user into a family of users. And each of those families of users can share a cached response between them. So now what we have is the user comes in with a cookie, that gets converted into headers, the application makes a decision based on those headers, and then sends it up to the CDN where it's cached, and it can be shared between that entire family of users, so it's highly cacheable. And that means most of the time you don't have to go to the back-end application. So those are two really big performance wins because you're not having to go so deep down the stack. But we do have a performance bottleneck here in pre-flight, but that's not so bad because it's just the one service. Or is it? That's what pre-flight actually looks like. It's like the rest of our stack. It's a big mesh of microservices. And that is all a performance bottleneck, every single bit of it. So what can we do to improve that? This game I call microservice whack-a-mole. That's the only GIF, so enjoy it. And the way you play this is you find the slowest service, you just keep hitting it until it's not the slowest service anymore, and you repeat. There's no exact science to doing that, but I can share a few tips. I won't be the only person today saying measure everything. We measure all our services' response times, and we make measuring really easy. So if you use our standardized tools for creating a service, then every HTTP request and response is measured at both ends. You really have to do something quite special to not measure stuff. You should try and be as granular as you can. So if you've got an application and there are two code paths through it, one of those code paths might end up contacting a different chain of microservices to the other. So there'll be vast differences in the measurements you make. So getting just a metric for how fast is my application probably isn't useful enough. So try and split your metrics along different code paths. Use medians and percentiles. If you use the mean, that tends to be thrown out by outlying values, so stick to medians and percentiles. And the last one is a bit of a gotcha. If you're measuring the timings of everything, timeouts, they kind of fall off the scale. They're the infinite values. So you can end up in a situation where everything that does respond is responding quickly, but the things that never respond at all, you're just not taking account of them. So make sure you count all your timeouts. So geography does make it have an effect on how long it takes to get somewhere. So if possible, keep all your servers in the same server farm or AWS availability zone. You'll get response times about 10 milliseconds if you do that, whereas if you go just a short distance outside there, it might be up to 50 or 100. If you can, host your application in multiple regions. The closer you are to your end user, the faster their response is going to be. And with that in mind, bugs in your routing layer can be quite tricky to find. They happen unexpectedly. So if you find some unexpectedly some responses taking a long time to come back, double check your DNS and routing layer to make sure there's no accidental routing something across the Atlantic when it shouldn't even leave the room. It's a bit of a vague catch-all heading. When you're coding, try and do as little as possible, wait for as little as possible. So pooling connections is a really useful thing to do. Every HTTP request has some overhead involved in that. If you pool your connections, then you don't need to do all those steps for every request. So in Node.js, the easiest way to do this is to use HTTP agents with keep alive. This is the easiest tip from this talk. If you do that in all your applications, it speeds them up massively. And there's probably similar things you can do with other protocols and other languages as well. Have a look at the responses coming back from your services and look for patterns. If certain families of requests always come back with the same result, then you can probably sort of poll for those common ones, hold it in memory, and then you don't need to make the request every time. And finally, find out if you really need to wait for the response. If you ask your stakeholders, product owners, whoever, does it matter if we don't get a response for this? Can I serve an error? Or can I serve just a default response? The answer might be yes. And finally, once you've got to a good point, regressions will creep in unless you stop them. So try and impose a perf budget, which basically means you agree with the business that if a request takes longer than a certain amount, you're never going to wait for it. I could probably talk for about 10 minutes about this, but I won't. But that link there is the document we sent to the board to persuade them that our paywall should time out after 200 milliseconds. So after all that work, the result is our paywall takes less than 20 milliseconds most of the time. It's never slower than 200 milliseconds thanks to the performance budget. And we have a really high cache hit ratio, which means our stack is more resilient and we save a lot of money because we can scale down a lot of applications. And I just realized I lied about the GIF. There's 2 GIFs. This is one of the perks of working at the FT. You get to go to the print room, which is really exciting. Okay, so that, on the flip side of that, we do pay a small complexity tax. It's a little bit more complicated than just having a normal request chain, but it's not too bad. And we didn't compromise on any of the principles, which were a really hard one. We still build with microservices, still release to production. It's still very easy to release pre-flight. But it's not always that easy. So this second case study, basically our front end, we wanted that to be performant. So a few fundamentals you're going to want any performant front ends to do. Try and cache and reuse assets between page views and between visits to the site. And there's lots of other modern best practices that you should aim to implement. So responsive images or critical CSS might be 2 of them. But ft.com, before we started to optimize performance, it was doing really badly at all these. So if you came to the site and visited a few pages, came back the next day, the chances are you would not be sharing any JavaScript or CSS between different types of page view or different days. And we weren't inlining any CSS. But there are good reasons why it was this bad. Because we've got this really distributed stack, lots of small changes happen all the time, and every time you build an app, the built assets will be slightly different, which busts the cache, so we can't reuse them. Build tools, they tend to generate assets which the app that's serving the assets needs to have some information provided to it by the build process. So that means our front end, which is roughly 12 microservices, 12 different builds, each of those page types served by each application only knows about the assets which were involved in its own build. So other applications, other pages cannot share those assets. And inlining CSS is a nightmare, even with a simple site. So it's no wonder that we didn't do it. So some potential solutions. We could pin our dependency versions. That might help. But we really like using assembler ranges. It gets a lot of bad press, particularly after the left pad debacle. But if you have loose Semver ranges, you're rewarded with it being very, very easy to roll out updates. For instance, you might want to change your copyright notice. So you just clear the cache and run a fresh build with a new version of the component. So if we were to pin our versions, it would take us a step away from our ideal of being able to release code easy and efficiently. Another option would be to ditch these 12 services serving our front end and just build a monolith app. But each of these services, they have their own glitches and their own problems. If you combine them into one, that increases the blast area, which again would make it harder to release our software. So for instance, our sign-up page app, the build process for that interacts with a load of dummy services for credit cards, which can be quite flaky. That occasionally stops us from releasing a new version of the sign-up page, but if we had a monolith app, it would stop us releasing the entire site. So in the end, we decided, well, performance is a big, complicated thing. We do need to build some kind of solution for it, and what we came up with was a thing called NUI. So this is roughly what NUI is. I won't read them all. It's kind of a mix of a CDN, a wrapped version of Express, a build process, lots of other things. And it enables stuff to be shared between applications, and which makes everyone very happy because now we've got a more performant site. And we still didn't compromise on everything. We've still got this distributed code base, everything's componentized, and we're still releasing very quickly. Then the reviews started to come in. I don't think I've ever been so unpopular with my colleagues. And the sort of painful irony with this is exactly what we were trying to get away from with the move away from Falcon. Falcon was really difficult to release stuff to. And we sort of tried to stick to our principles, but we ended up messing everything up anyway. So this is where the group therapy starts. This is where I start to make some confessions. So what did we do wrong? What did I do wrong? So optimizing performance, we had a team of 2 people, and we're probably a bit too isolated from the rest of the team. It became a little bit of a bubble, we weren't talking to people enough, and we lost sight of some other things that are important. So pre-flight, those 2 diagrams I showed earlier, added a bit of complexity, but lots and lots of value. NUI, on the other hand, added a lot of complexity and some value. And then, so there are various features. They add some complexity and difficulty to your stack, but they might speed things up. So on this chart, some of the things add a lot of speed, not much complexity, and some of them the opposite. We just kind of became a bit of a performance cult, and we just went for all of them, regardless of how difficult it was. We didn't really take into account that some of them would make life painful for our colleagues. This is my controversial slide. I thought I should put one in. So performance, and I think we probably all think it should be, but it's not a core skill. You can have a very successful web development career without ever learning much about performance. It's not taught in code boot camps because they don't really have time to teach it when you're teaching all the other fundamentals. So that's where we're at with our team, that it's really an area that not many people know much about. And we didn't really take enough consideration of that. So I read a really nice blog post by Malte Ugel the other day. Hope I'm saying his name right. It talks about the programming model, how the choices you make about abstractions and APIs really have a big impact on how your team work. And in making these choices about abstractions, you should demonstrate a lot of empathy to the people who have to use them. And we just lacked empathy, and we didn't think enough about the end user. So here's a particularly bad example. So before NUI came along, in your source file, if you wanted to use a style sheet for a component, you just imported it. Simple. After NUI, you have to register that component with a central configuration thing. You have to add in the component itself, you have to add loads of mixin calls, and then you include it with a particular mixin to do some overrides. And finally, you import a final file which outputs the styles, which is just really confusing. If you compare the two, it's just a massive, it ruins people's ability to write style sheets. And then after kind of realizing how bad a job we'd done, we came up with this, which is if you don't use that, that mix-in, basically splits your style sheet into pieces and inlines some of it and doesn't inline other bits. That's totally optional. You can still write styles as you're used to writing and not use that at all. If you do choose to use it, it's a far lower level API, which is more flexible, more powerful, and gives more control to the person actually writing the styles, which I think is a much better situation than there was before. So, looking for some general principles and what we did wrong, and then how we started to make things right. Initially, performance optimization is complex, and people don't know too much about it. But we took the decision of hiding that complexity rather than teaching people about how to work in this environment. We went with some abstractions which were quite clever, but that just adds another layer of complexity. Sooner or later, those abstractions are going to leak. People still need to learn the underlying code, but they also have to deal with your horrible code. So a bit of syntactic sugar to remove the repetition of writing performant code is nice, but don't do anything too weird. We tended to kind of huddle together the people who knew about performance, the very experienced developers. We didn't talk enough to our more junior developers. So of course we're going to write something that's really difficult to use. And finally, we just kind of had all these ideas, built a thing, and then just went, there you go, there's performance, have it all. When we should have probably gone for an approach of solving each performance problem one by one and trying them out with people, which make it easier to roll back from the bad mistakes. And these principles, I think they apply to retrofitting all kinds of things to your code base. And the sort of general principle here is weigh up the pros and cons of implementing any performance optimization. No one's holding a gun to your back saying, you must do a service worker. Just work out if it fits with your stack and with your team, and don't just impose it on people when it's adding too much complexity for the wins that it gives you. So in conclusion, blue slide, releasing code small and often has really great benefits. It's transformed how we deliver ft.com. Really recommend this approach to anyone. Performance optimization doesn't necessarily sit well with technical choices you've made for other reasons, particularly in a very distributed system. You should work with your team to find out what's the right balance between adding this performance complexity and what they can absorb, and don't become a bit of a performance cult just chasing every tiny millisecond gain. And you really don't have to be perfect to get great results. We've messed up quite a bit, but we're still one of the fastest media sites in the world. So yeah, just do what you can and don't worry about being perfect. That's all. Thank you.